In this video, I'm going to give you a beginner-friendly introduction to the PyTorch library and how we can use this library to create a neural network that can do handwritten digit classification. So without further ado, let's just dive right in. So these are the libraries that we're going to use in this project, and you'll have to download those using either pip or conda. So you download the Torch library, Python library, by going to their website. There you can see the command that you have to type into your terminal in order to download it. And I use Python 3.12, and I'm sitting in a Windows Linux subsystem. So the first thing that we're going to do is that we're going to take a look at the dataset that we're working with. We're working with the MNIST dataset. So let's just try to import it. I've already downloaded it and saved it at this path. And what we can see is that the first column contains the labels. So what digit is it? This is a 1, this is a 0, and this is a 4. And the rest 784 columns, they contain pixel values. So each image contains 784 pixels. So therefore, our neural network will have to have an input of 784 neurons. So let's define our neural network. We do this by defining this class that uses this NN module from PyTorch. And then we can start in the self.layers variable. We can start by creating the architecture for our neural network. This is a quick introduction to neural networks. This is the input layer. In this case, this is the image, and every single pixel value, so that is the value for each input neuron, is used to calculate the value for the next neurons in the hidden layer. And this is the output layer, where the highest value is the neural network's prediction. So how are these activation values actually calculated? So this is a very simple example where there's one neuron that goes into a neuron in a hidden layer. And the way it's calculated is that you have an activation function, then you multiply a weight with the value from the previous neuron plus a bias. And it is these weights and biases that you tune for the model to be able to correctly classify the digits. So each of these arrows represents this value from the previous neuron and a weight. And there are different weights for every single arrow, but there is only one bias for each neuron. So when you have a neural network that contains multiple neurons, the values of these next neurons are calculated in the same way, but you just have to sum up the calculations done for each of the previous neurons. So you have the weight that comes in this arrow, you multiply it with the value here, and then you sum that with the value that comes from this arrow, which is a different weight and a value for this neuron. And then you add the bias in the end, and then you use a activation function. That could be a sigmoid or ReLU. It's the same calculation for the other neuron, except for that it's different weights, right? But it's the same activation value that comes from the previous neurons. So in order to make the neural network able to correctly classify the digits, we have to use the backpropagation method, which is what you use to tune these parameters, the weights and the biases. In the end, it's always just a long mathematical equation, and we just have to find the correct weights and biases that will make the neural network classify the digits correctly. So what we do is that we create a linear layer that contains 784 neurons, that's the input, and then we can decide what should the output be, what should the output to the next hidden layer be. And we're going to have one hidden layer that contains 64 neurons. So therefore we go from 784 neurons into 64 neurons in our hidden layer. Then we have to decide what kind of activation function that we're going to use when we calculate the activation values for each of these neurons. And we are going to use the ReLU activation function. We could also use the sigmoid. The ReLU has just been proven that it produces better results. So that's why we use ReLU now instead of sigmoid. And then we have to decide the output layer. And the output layer should be the number of digits that we can classify, right? And we can classify from 0 to 9, so that is 10 different digits. So therefore we put 10 here as the output. And it takes in from the 64 neurons in the hidden layer, it goes into 10 output neurons. So that's why we have 64 here and 10 here. So now we've created the architecture for our neural network. Then we define the forward, which is when the model has to calculate an output. Then the X, this will be our image. That will be inserted into the 784 neurons. And then it will just go through the neural network, and then it will produce an output. Now that we have the architecture of the neural network and an understanding of how the data looks, we can start by creating our training and test sets, because we have to have a training set and a test set, and a test set has to contain samples that the model has never seen before. That's the only way we can actually determine how well our neural network performs on unseen data, how well it generalizes. So we're going to use the train test split function that comes from the sklearn model selection library. And that allows us to give this data frame of the data that you see here. Then we can decide the size of our test set. And we are just going to use 20% as a test set. And we can actually just check how many samples do we actually have in this data frame. So there are 42,000 samples in this data frame, and we use 20% of them as testing. And then we put a random state of 42 so that whenever we run this code, it's the same output every time. And then we use stratify on the data frame on the labels. And what this means is that we keep the distribution the same, so that the training samples and the test samples, they have the same distribution of digits. So let's see here. If we run this code, we see that the data in the training set uses this distribution, and if we just change this to the test data set, then we see the same distribution. So, and this obviously also helps the model learn all the digits. If the training samples only had 0 or 1 digits, then it would never be able to classify a 9, and so on. Okay, so we are going to define this class, the MNIST CSV, because now that we're ready to moving closer to being ready to train the model, we have to be able to pull out a single sample from this data set. And we do that with this class. So we define the constructor that has the labels, and that is just the first column from the data frame. And then we have the pixels, and those are the remaining columns in the data frame. And you define that like this. And then this is just the length of the labels. And then this get item, which is what actually picks a sample from this data frame. Then we can run it. To get the trained data set and the test data set, we just switch out these values, these variables, to get the different data sets. And then we can use the data loader, which is what we use when we train the model, because this allows us to use batches. So this data loader will take the training set, data set, and every time we call for new samples, it will give us 64 new samples. Okay, so now we're ready to train the model. So what we're going to do is that we are going to define this criterion. That will be our loss function. And the loss function is what you use when you fine-tune the parameters in the neural network. So all the weights and biases. And we are going to use the cross entropy loss, because that's just once again been proven to be a good loss function, especially for this type of problem. we're going to use the atom optimizer and a learning rate of 0.001. And the atom optimizer is what is responsible for optimizing our weights. Next, we have to define how many epochs we want. And an epoch is when we run through the entire training set once. That's one epoch. And we are going to run through the entire training set 10 times and log the results. So we set the model into training mode so that it's ready to tune its parameters. Then we use the train loader and we get the inputs and the labels. So for each inputs and labels, that means since the train loader uses a batch size of 64, this will contain 64 different samples. And there's no optimized reason why we use a batch size of 64. We could have used 32. This is not to get the absolute best results. This is just for you to get an understanding of how you can train a neural network model or any other model. So the reason for batch size is that we make the model, before we tune any parameters, we make the model create predictions for 64 samples, and then the model calculates the gradients via backpropagation, and then we take the average change and changes the weights and biases using these 64 samples. And that makes the model train much faster, and it's shown to perform very well. And that is versus training where we take one sample at a time and do backpropagation for every single sample. Instead, we can do a batch size and take an average step with this batch size of 64. Okay, then we feed the inputs to the model to get the outputs. And then we take our criterion, which is this loss function, and then we take the outputs and give the true labels, and then the model decides how wrong it was for this step. Then we have to just reset the gradients from the previous step before calculating the new gradients for this batch. Then we take the backward step, and the optimizer takes a step, updates the weights and biases, and then we save the loss and we can print it out. So let's just try and run this. So as you can see, it runs pretty fast, and this runs only on the CPU, not on the GPU. All right, and now it's finished, and as we can see, the training loss doesn't really matter. The important thing is that it keeps dropping. And what you have to remember is that if you do too many epochs, this could hurt the model, because then we start overfitting. And what that means is that the model just learns exactly what's in the training samples, and it doesn't generalize. We want it to generalize to data it's never seen before, so therefore you have to be cautious when you increase the number of epochs. So now we're ready to evaluate the model on test data. So let's just run this method, and as we can see, we get a 94% accuracy. So what it does is that it takes the inputs from the test loader, calculates some outputs, and then for every output the neural network makes, every digit will get its own value, and the model will pick the digit with the highest value, because that's the digit the model is most sure this image represents. Yes, and here we can just, for fun, just look at the labels, let the model create some outputs, predicted, and then we can see here just for a single batch where it might go wrong. So it predicts this correctly, this 8, this 6, oh, here is a 9 and an 8, and the true label is a 9, but we predicted an 8, which is wrong. So that's just one error. And there are probably other errors, but yeah, you get the idea. So I hope you enjoyed this video and that you now have a much better understanding of how you can create a simple neural network. In my next video, I will code a neural network from scratch, so without any libraries, and I will code backpropagation from scratch, and it will be GPU supported, and it will run very fast. So I hope to see you in my next video.